Hi. Earlier today, I gave a solution to a question involving motion in a plane. So the question was Ekalavya, who is 12 meters away from a mango tree, takes aim directly at a fruit hanging at a height of 5 meters. Just as he shoots the arrow, the fruit drops and the arrow strikes the fruit after zero point 0.8 seconds. Find the initial speed of the arrow. Now, earlier I shared a method where you wrote the coordinates of arrow as well as the fruit at time t, at a random time t, and then you equated the coordinates to get the answer. This was a lengthy method, but it gave you the answer. Now we will be looking at a better approach to solve the same problem, and this approach involves relative motion. So we'll actually understand how we can exploit the idea of relative motion and relative accelerations to solve this problem in probably one step. Yeah, before that, let me erase this method from here. This is no longer necessary if we are planning to solve this problem through relative motion, which is a much better approach and recommended if you are doing something in a short period of time. Yeah, just a minute. Let me just complete this. I just wanted the solution to be there so that you will get an idea like how lengthy the approach was, in case you have not seen the other video. Now again, we come back to the question. Now we use the concept of relative motion. We know that both the arrow as well as the fruit is in the same medium. Both are in the same medium. So the acceleration 10 meter per second square, which is g, is common to both of them. So in with respect to the arrow, the acceleration of the fruit is 0. So this is the idea which we will be exploiting. That is, you know, velocities are relative, and if you add a certain amount of velocity to one object and you add the same thing to the entire universe, the situation is the same. Similar is the case for accelerations. So what I will be doing is, I will be adding an acceleration of 10 meter per second square to each and every body upwards. So this will effectively cancel out the acceleration due to gravity. By adding 10 meter per second square, we are not only adding it to the arrow or the fruit, we are adding to everything. That is Ekalavya, the ground, the tree, everything is accelerating upwards with 10 meter per second square in our frame of reference, or to be precise, in the frame of reference of the arrow. What is the benefit of doing this? Actually, it's a huge benefit, as the entire process of calculating the coordinates disappears. You only need just one step to solve the entire problem, which is, once acceleration is added upwards 10 meter per second square, taken relative to the arrow, the net acceleration becomes 0 of every body. Therefore, what happens is, the fruit which was initially at rest 0 meter per second square, it gained velocity because it had a component of vertical acceleration downwards. But once we added the 10 meter per second square acceleration upwards, acceleration became 0. So the velocity remains 0, implies the fruit does not fall. It remains on the top of the tree. And the arrow, horizontal velocity component doesn't change, but in the earlier case where we did not use relative motion, the vertical velocity component changed. It decreased due to the acceleration downwards. Velocity upward direction decreased, downward direction increased. Okay, but once we added the 10 meter per second square acceleration upwards, velocity doesn't change. So from a problem of Galileo's equations of motion, which involved acceleration, we come to a problem of uniform velocity, uniform motion, no acceleration. So in this case, with respect to the arrow, acceleration equal to 0, both fruit and arrow. So now the velocity component v, horizontal velocity, what is it required to do? It is required to cover 12 meters in how much time? Let us assume t seconds. So v into t equal to 12, and actually t is 0.8, because in 0.8 seconds it hits the fruit, and the fruit is remaining at rest on top of the tree. Therefore the dimensions are unchanged, hence 12 meters is the distance, and thus substituting we get vh equal to 12 by 0.8, which is 120 by 8, which is 15 meter per second. I believe this is the same answer we got in the earlier video where we did the long approach. Now again, the vertical motion, you need not include acceleration, second law, that is Galileo's second equation of motion, nothing is there. Simply v vertical into the same 0.8 seconds should be the distance covered, which will be equal to 5 meters, because we are assuming Ekalavia doesn't have any height. So from the ground 5 meters above is the mango, which is not falling. Therefore the arrow must cover 5 meters in 0.8 seconds with the velocity vv. Therefore we get directly v vertical equal to 50 by 8, which is 6.25. Again, exactly the same answer we got in the earlier method. So we just now understand how powerful the notion of relative motion is. Relative motion is actually an extremely beautiful concept, and if used in the proper way, it can simplify problems greatly. Hope you enjoyed it. Thank you.